All right, so welcome back to from spring break, and today we are mainly going to be talking about shadowing. Okay, and before we start, I want to make a correction to what I said in the last lecture. There is one thing that I said that was not correct. That was basically the formula that the dimension that computed from the Lyapunov exponents is equal to the box counting dimension. It's actually not correct for all uniformly hyperbolic systems. So you can prove it for a subset of systems, for example, systems with only one stable direction, and you can also prove it for systems that are sufficiently mixing, but like it's not for all hyperbolic systems. All right, so that's one correction I want to make before we proceed. All right. Okay. So today we are going to be mainly talking about what is shadowing. And I'm going to first of all discuss the definition of shadowing and give an example for the sawtooth map. And then I'm going to be talking about the implication of shadowing. And then I'm going to basically really introduce a misunderstanding that has traditionally been associated with shadowing. So let's start with shadowing and why it is important. Okay, shadowing on a high level basically says that if you have a chaotic system, and if you compute a trajectory of an inexact version of the system, then there is a trajectory of the exact version of the system that stays very closely to the inexact solution. Okay, so as you can see, it has a very clear or seemingly clear consequence on the motivation we gave on the first day of our class. That is, if you do a numerical simulation, right, and make some error, how does that numerical simulation reflect the real how does it reflect the behavior of the real system? So basically, let's introduce the concept of a pseudo orbit. So a like epsilon pseudo orbit, right, of let's introduce it in the concept of a map, of a map phi, right, like phi, it's a map from the phase space to itself, right, is a solution, is a trajectory, like x1, x2, etc., that satisfies xk plus 1 instead of exactly equal to phi of xk, right? It satisfies the difference between xk plus 1 and phi of xk has a norm less than epsilon. All right. In some basically intuitive word for it is that it's a solution that satisfies the system with the precision of epsilon. Okay. Now that actually introduces, that definition allows us to introduce the what does it mean by a dynamical system having the shadowing property, right? Like a system has a shadowing property, so phi has we say the infinite time shadowing property if, so for any epsilon greater than 0, so this epsilon can also, for any epsilon greater than 0, there exists a delta, okay, such that for every delta pseudo orbit let's say x1, x2, etc. There exists there is a precise orbit. There is a x1, y1, y2, etc. that satisfies the exact equation. So yk plus 1 is exactly equal to phi of yk. And the difference between xk and yk is always going to be less than epsilon for all k. All right, so maybe we should translate it into intuitive words, right? These mathematical statements. So that is saying that, let's say if you want, so epsilon is anything, right? So basically, if you give me a requirement, okay, the requirement being how accurate you want the solution to be, okay, then I can give you a delta. There exists a delta, right? That I can give you a delta and tell you perform a numerical simulation with the precision of the governing equation or with the residual of your convergence being better than delta. Then you are guaranteed that your solution is as accurate as the epsilon you have put as a requirement. The solution being as accurate as epsilon means that there exists a real solution. So the y is the real solution, right? That you don't know what it is, but you know it is close to the numerical solution you get with a precision of epsilon, right? So that's what the shadowing, this is called the shadowing. The shadowing lemma basically tells you that a system would have a shadowing property if it satisfies a actually surprisingly simple set of properties we call a uniform hyperbolicity. So basically, we'll introduce the what is exactly uniform hyperbolicity later, but it basically says that you can decompose the system into a stable set of equations and an unstable set of equations around the neighborhood of any trajectory. Okay, so we'll first look at it for the sawtooth map, which we started looking at the week before the spring break. And we'll see that the shadowing property is almost trivial for a sawtooth map like that. Okay, any questions about the definition first?
So what exactly is, I may have missed it, what's the actual physical mechanism that's shadowing is?
What is the physical mechanism of what shadowing is? We'll exactly illustrate that through two examples.
Okay.
All right, okay. So I'm going to show you two examples. One example is an example of a stable system. So this is a phi of x, this is x. And the phi of x, I don't know what it is, but it is a map that has a slope of less than 1. So it is a stable system that converges to a fixed point where this line intersects with the 45-degree line, right? So this is the fixed point. Okay, what the shadowing solution means in this case is almost trivial, right? So what it means is that if you are able to perform a simulation, so if you perform a simulation where you are following not exactly this phi of x, but to deviate from it a little bit, okay, then how can you find the pseudo solution y? So if you have a x1, x2, etc., right, that satisfies satisfies this property with right. So let me just call it delta, right? I mean, it doesn't matter. So if you satisfy this property, how do you find a real solution y that satisfies exactly the same equation? Any ideas?
did some stuff with getting out the normal component of a perturbation before, so is it kind of the exact same thing? So that keeps on have the same trajectory?
Mm.
With the time dilation stuff?
With time, yeah. So the time dilation stuff is actually very relevant if we're looking at a periodic system, right? So here we're just looking at a stable system. Yeah, if you have a stable system, right, what is the solution like? Actually, what is any solution that satisfies the exact equation like? If you have a unique fixed point.
Just go to the fixed point?
Exactly. So the solution just goes to the fixed point, right? So essentially what you have is that no matter what x is, no matter what the pseudo solution is, the real solution y is a solution that basically keeps tracking into the fixed point. Okay? So then if you want a delta pseudo orbit, if you want to exact orbit y that shadows this pseudo orbit, you can just start with y1 equal to x1 and keep doing the simulation, right? Then what happens is that all the y case is going to converge to the y fixed point. So why does it satisfy the shadowing property? Why is the real solution that converges the fixed point shadows the pseudo orbit? That's because no matter if you're introducing only a small perturbation, right, to the governing equation of the pseudo orbit, then because the system is stable, that pseudo orbit, that numerical solution or perturbed solution, is also going to be just roaming around the stable fixed point, right? That's because of the stability of the system. So, for example, if the slope of the map phi, right, is less or equal to some a, which is less than 1, right? Let me just say the absolute value of phi prime, the derivative, is less than or equal to a. So a is the maximum slope, which is going to be less than 1 for the system to be stable, right? Then what happens is that if you start with y1 equal to x1 and look at its difference, right? So the error, so let's say define the error being yk minus xk, right? Then because the derivative of phi is always less than a, right? Then what happens is that the ek plus 1, the next error, is always going to be having an absolute value less or equal to a times the previous iteration error, and then plus this plus the delta plus the error you're introducing in this iteration, right? So basically what it says is that if you had an error of e in the previous iteration, the resulting, the cause of the error to the next iteration is going to be shrinked by a factor of a, right? And you are introducing an additional amount of error delta in this iteration because y is an exact orbit and x is a pseudo orbit, right? The governing equation differs by delta. Therefore, the next iteration has an error that is bounded by a times the error in the previous iteration plus delta. All right, make sense? So if you keep doing that for infinity, and if you start with a 0 error, right, E1 is equal to 0, then you can prove that for all E, it's going to be less or equal to delta divided by 1 minus a. Okay, this is easy to prove because if in the previous iteration this is true, and if you move to the next iteration, you multiply this thing by a, and you add a delta onto it, right? Delta plus this thing times A is going to be less than or equal to exactly the same number. All right. Any questions? So essentially, that proves our statement. If you give me any epsilon, right, I'm going to for any epsilon, I'm going to give you a delta that is equal to 1 minus A times epsilon, right? So that's my recipe, that if you keep your simulation accuracy to be below this value, I'm going to be guaranteed that your solution, your numerical solution X, is going to be differing from this particular real solution by less than delta over 1 minus A, which is exactly epsilon. All right, make sense? Any questions about this particular example? So a stable system, right, that has a really a stability constant, has a slope of exactly strictly less than 1, is always going to satisfy the shadowing property. Okay, so this is for a stable system. How about an unstable system like the sawtooth map? Okay, so for the sawtooth map, remember, like, we are looking at the interval from 0 to 1. It maps to the interval 0 to 1, but with a slope of 2, right? So why does the sawtooth map also satisfy the shadowing property? The same recipe for the stable system does not work, because if you set an initial condition to the same as the initial condition for the pseudo-orbit, then because of the butterfly effect, okay, because the slope is greater than 1, the error, instead of being diminished by a factor of A, it actually gets multiplied by a factor of 2, right? So the difference between the pseudo-orbit and your constructed exact orbit would actually keep amplified before it reaches order 1. So you cannot construct a real orbit like that. Instead, the best way to construct a real orbit is actually going exactly backwards. Okay, so let's say if you have a pseudo-orbit x1, etc. to xn. Instead of starting from x1, I'm going to start from xn, and I would say yn is equal to xn, and then I go backwards. Okay, so in this case, for every yn, I can find 2 different yn minus 1s that maps to the same yn, right? So this is the phi of yn, and this is yn. For every yn plus 1, I can find either this one or this one that satisfies the system. But I'm going to be choosing whichever one that is closer to x, the corresponding x. All right. So if I keep doing this, I'm going to be all the way getting a solution that exactly satisfies the governing equation, right, all the way to y1. And why is it a shadowing solution to x? Because of exactly the same argument as the stable case, right? An unstable system is stable with a equal to half, right? So essentially, by just going backwards, I can show that for any epsilon, if I take delta equal to half of epsilon, because the a corresponding a is half, right? The inverse of the map has a slope of half as opposed to 2. So that's going to give me a shadowing solution that has a distance less than that particular epsilon. All right. Make sense?
So you first simulating this forwards to get all your x's, and then you try to figure out your y's.
Yes. So first, your simulation for the pseudo orbit goes forward, right? So for every step, you are making an error with a bound of delta, okay? And then to find out the corresponding shadowing solution, you go backwards, start from the last iteration, and you go backwards with the exact solution. Okay, with the exact map. Okay, so we're going to actually use this construction to study shadowing solutions later. But this pair of examples also is a good recipe to tell you what kind of systems would have this shadowing property that is true for infinite time. So there is actually an array of different shadowing properties. This is really the infinite time shadowing property, meaning that no matter how long the trajectory is, right? So if n can be 100, a million, or a billion, you can give the same delta for a fixed epsilon you give to me. Right, so in this case, delta is always equal to half of epsilon, no matter how big n is. There are other weaker shadowing properties where the delta could depend on both epsilon and the length of the trajectory, right? As long as the delta doesn't grow too fast as you make the trajectory longer and longer, we also call it the system has a weaker type of shadowing properties. Okay. All right, so the system that has the infinite time shadowing property is really this kind of systems that could be thought of as a combination of a stable system and an unstable system, right? So for basically in the neighborhood of any trajectory, you can always think of there is the neighborhood that can be composed of a stable direction and an unstable direction, or like a stable subspace and an unstable subspace, right? If you perturb in the stable subspace, the perturbation is stable in the sense that if you evolve forward in time, the perturbation is going to come back to the solution. If you perturb in the unstable direction, then that unstable direction is actually stable backwards in time, right? Just like how we are able to show the shadowing property in the unstable case. And any perturbation in the neighborhood can be actually written as the sum of a perturbation in the unstable direction, in some unstable direction, and in some other stable direction. So that is what a uniformly hyperbolic system is. All right. Okay. Now let's actually keep these examples in mind and think about what is the implication of the existence of such shadowing directions. So remember, like in the beginning, we thought of a chaotic dynamical system as having two types of potential applications. One type of potential application is for you to forecast what the system is going to be doing after a finite amount of time. So a typical example is the weather forecast, right? We want to know what the weather is like a week from now. The second type of applications of chaotic system is more about the climate rather than the weather. So that is, the horizon of your prediction is much, much longer than what is implied by the highest Lyapunov exponent, right? Or the horizon of your forecast is much longer than 1 over the maximum lambda. So what does that mean? So the Lyapunov exponent is a measure of time scale. It has the unit of 1 over time, right? So if your time scale forecast, for example, if you want to think about how the climate is going to be like 10 years from now, we know the weather has a Lyapunov exponent on the order of like 1 over a week, right? So if you look at the weather forecast much more than a week, it's going to be completely off. So what does it mean by trying to forecast the system for much longer than a week? It means we are looking at statistics rather than the instantaneous solutions, right? It means we want to look at quantities that are averaged over a time period much longer than what is implied by the largest depth of exponent. So when we say we want to forecast the climate in 10 years, we don't mean that we want to know exactly what temperature Boston is, right, 10 years from now. We want to think about if you average over a year, what the temperature at every location is likely to be. So this is really looking at statistics, or we are really thinking about J bar, which is defined as mathematically, it is really a limit of t goes to infinity, 1 over t, right? A summation of I goes from 1 to t if you are looking at the discrete maps of some j as a function of x at iteration I, right? So this is the kind of objective function we are looking at. Now, the problem with a numerical simulation is that we are always going to be obtaining a pseudo solution or a pseudo orbit rather than an exact solution, right? Because there are two ways to look at it. One way is that we think about our numerical solution or model as the phi, which we can express as a formula in the computer. And the real world is a pseudo-orbit, right? Because the real world may not have any governing equations, or at least governing equations of the same phase space as we are representing in the computer, right? It might have some governing physics, but at a much higher dimension than what we can express in a computer. The other way to look at it is that the real world has an exact governing equation, phi, and what we can represent in a computer is a much reduced or much approximated physics that we are basically, either way, either the real system is a pseudo-orbit or computation or simulation is a pseudo-orbit, and the other is the exact solution. Okay, so in both cases, we are obtaining something different from reality. And the question is, if you look at the J bar computed between a pseudo-orbit and an exact orbit, right? Or you're looking at 1 over t of the J's computed over a y, a solution y, where x is a pseudo-orbit, y is an exact orbit. What is the difference? So shadowing actually potentially can give you an answer to that. Okay, so because if j, the objective function, is a smooth function, right, then the difference between, let me say, j bar prime is equal to that. Then the difference between j bar and the j bar prime is going to be bounded by, so let's say, if you can introduce, say, a norm saying that like j, if you can bound the difference in j by some b times the difference in its independent variable, right? Then that the long time average can be also bounded by the same b times the maximum potential difference between xi and yi, right? Which in our shadowing lemma, this is going to be less than b times epsilon. So essentially what it tells you is that if you want your long-time objective function, right, long-time average, the climate quantity, to be accurate to a certain precision, then you can always have a delta for which you can guarantee that as long as my numerical simulation, as long as my modeling accuracy is better than delta, I can ensure that the solution error, right, which is measured by the statistical quantity, is less than that requirement, epsilon. All right. So that is why there is a lot of a lot of people believe that this pseudo orbit tracing property is really the infinitely long time shadowing property we just presented in the last slide, right? So that is a restatement is that for any given epsilon, there exists a d such that for any d, so d is our delta, right? A d pseudo orbit, there exists a solution, right? A trajectory that satisfies the real physics that's represented as phi. That epsilon shadows the pseudo trajectory. Okay, so this pseudo trajectory here is our x, and this point x is the true solution we just wrote as y, right? Okay, so it says from a numerical point of view, if phi has this infinite time shadowing property, then numerically obtained trajectories on arbitrarily long time intervals reflect the real behavior of trajectories of the real system. So that's the traditionally accepted implication of shadowing. And actually, this lecture, what we are going to show is that this traditionally accepted implication should be called into question. It's not really correct all the time. Any questions over here? Like why this traditionally accepted view is thought of as correct? It has to be having the infinite. So this is the easiest way to see this is that this is true for infinitely long shadowing systems, right? And that can be proved for uniformly hyperbolic systems. But for systems with actually sufficiently long shadowing solutions, this can also be correct in the sense that if so basically, instead of this averaging being uniform, if only occasionally if x and y differs only occasionally for much higher values, this can also be correct, right? So basically, it depends on the definition of shadowing. If the uniformly shadowing property ensures that x and y differ never by more than epsilon. There are other shadowing properties for which x and y differ most of the time by less than epsilon, statistically speaking, and there is a small enough tail that you can still guarantee that the difference between the objectives when averaged over infinitely long time is still less than like a certain thing, right? So that can also be the statement is also correct for that kind of shadowing systems for which can be not uniformly hyperbolic, right? For example, the Lorentz equation at standard parameter values is actually not uniformly hyperbolic, but it does have a strong enough shadowing property that this is still true. All right. Any other questions? Okay, so let's show that what is the assumption, the unspoken assumption of shadowing-based statistical stability. So this statement over here, right, is really statistical stability. That is saying, if I perturb the system by less than delta, then the statistics would differ by less than epsilon, right? A small perturbation leads to small result. That's a stability statement, okay? So the unspoken assumption is really that for any pseudo orbit you obtain, although there is a exact solution, but that exact solution has to be able to represent the statistics of the system, right? So Okay, so if you read the line, like it reflects the real behavior of trajectories of phi. But are all trajectories of phi identical in terms of the behavior, or in this case, in terms of its statistics? There is a very simple counterexample of our previous case, right? So if you again think about the sawtooth map, remember when we perform a naive numerical simulation of the sawtooth map, we did not reproduce the long-term behavior of most of the trajectories, right? We actually converge to this single point zero, right? So if you remember our previous example here, I think it's probably the first one, right? So if we randomized a bunch of, if we just get a random point and we follow the sawtooth map for a long time, all the solutions converge to zero. And that is because when we randomized a initial value in the computer, we obtained a value that is actually has finitely many digits in its binary representation, right? That is not almost any solutions, right? Almost any value within 0 and 1, almost any real values, not only would have infinitely many digits, it would also have independent and identically distributed digits that with half probability of being 0 and half probability of being 1, right, in its binary representation. So here we are actually getting a special trajectory that has remarkably different statistics than what can be proven as being uniformly distributed between 0 and 1, right? So this is what we ended up simulating with just expanding the domain from 0 to 1 to 0 to pi, right? We get the uniform distribution. But if we do the simulation between 0 and 1, right, with a computer representation of numbers, we get a long-term trajectory that are just all 0 most of the time. So this assumption that there is a unique real behavior of any solution that satisfies the same governing equation, it's simply not correct, right? So essentially there are what we call physical solutions. And there are, of course, not physical solutions or unphysical solutions or non-physical solutions. So what are physical solutions? What are non-physical solutions? We have to really define them, right? A physical solution is a solution, right? A physical solution is a x1, etc. That first of all, its long-time behavior exists, right? So has a long-time behavior, has a well-defined long-time behavior. So any objective function j bar, there is a limit of t goes to infinity, 1 over t of summation of j of xi, okay? And if you perturb the initial condition, if you perturb the system a little bit, and for almost any perturbation, small perturbation, small enough, or in mathematical terms, there exists a neighborhood of x1, right? And for any almost any perturbation in that neighborhood, for any small perturbation, x1 plus this perturbation, right? Perturbation. Okay. Let's call it the x prime one, right? Then this, and if you follow the same, exactly the same map or same dynamics, then I would get exactly the same j bar. xi prime, which is going to be the same, right? We get the same statistics. So this is called the physical solution because that's what you would observe in a laboratory if you actually able to do the experiment, right? So let's imagine this this dynamics phi is actually what the real world satisfies. Then when you do an experiment, you are not going to be starting from any exact particular initial condition you choose in your laboratory, but most likely some perturbed initial condition, right? And for almost any perturbations, right, you should actually get the exact long time statistics. Any initial condition for which the long time statistics would differ from almost any perturbed initial condition should never be observed in a laboratory. So this is what a physical solution is defined as. So what is a non-physical solution? Well, of course, a non-physical solution is any solution whose initial condition does not satisfy this property, right? For example, if you start the sawtooth map exactly from 0, right? Exactly from x1 equal to 0, then your x2 is going to be 0, x3 is going to be 0, and all your solutions is going to be 0. And your statistics, your J bar, would be different from any perturbed initial condition, right? If you perturb initial condition to almost any value around this 0 point is a number with infinitely many digits, right? Although you may have 10 digits being 0, starting from the 11th digit, you may have random values, but even from that, you are going to be getting a solution whose statistical distribution over the interval is going to be uniform, right? It's different from your initial condition. Okay, so now we know that there are physical solutions, there are non-physical solutions. Let's think about what are the type of non-physical solutions. So the non-physical solution, we have just looked at one non-physical solution, right? The non-physical solution, type 0 is a steady state. Just like the 0 point. But it is a steady state, but in a chaotic system, a steady state is always an unstable steady state, right? If you perturb it, you are not going to be fixed at that point. It's a fixed point, right? It's an unstable fixed point. This actually exists, and people did find it, even in large-scale systems like fluid flows. So if you have a high Reynolds number fluid flow, you can actually use some special numerical techniques to find the steady state solutions that you will never observe in a laboratory, right? So you can find the steady state, usually laminar solutions that are just unstable. If you initialize the solution, like in the unsteady simulation, you're gonna see it becomes unstable, it'll start vortex shedding, and it may transition to turbulence. But if you use a very strong solver, you can actually get sometimes you can actually get a steady state solution that satisfies the Navier-Stokes equation at every single point, right? So that can be computed, but it is one of the non-physical solutions, of course, because the statistic is going to be different, very different from what a real solution would be. Okay, and there are also other non-physical solutions. So this is type 0. Type 1 is periodic cycles. Again, in a chaotic system, the periodic cycles again would be unstable periodic cycles. If you perturb the initial condition a little bit, the periodic cycles would become non-periodic. So what is an example of a periodic cycle in our sawtooth map? Anybody remember we did derive some examples. Right, remember the sawtooth.
Like a half to like 1 to 0 to a half, that kind of thing.
1 to 0 to the half. Can you say again?
There was like one cycle that we, like perfect cycle of the Baker's map that we did that basically went from.
Yes, that perfect cycle is 1/3 to 2/3 to 1/3, etc.
Right. Yeah.
Yes. So why is that the case? Because the sawtooth map maps from xi, which is 0. Let me just represent any xi as a bunch of binary digits. Let's represent the first digit as xy with the superscript 1, right? Xi with the superscript 2, etc. Right? Let me just use this to represent. Let's use the superscript to represent which digit after the binary point it is. Okay. Then xi plus 1 would be actually a shifted version, right? It's actually going to be a 0.xi2, xi3, etc. Or in some other sense, xi plus 1 with a superscript k, it's actually going to be equal to xi with a superscript of what? K plus 1, right? So the kth digit of the next iteration is going to be the k plus 1th digit of the previous iteration. All right. So now if you think of that, it's easy to construct a periodic cycle, right? For the previous example, my xi is just a 0.01010101, right? Every time you shift and shift again, you get exactly the same number. You can also construct numbers that has period of 3. That's simply 0.001001001, right? Or 011011101, etc. So you can construct any length of period as you want, as long as you get an initial condition whose digits repeat with the period of n. You get a dynamical system. I mean, you get a trajectory of the dynamical system with a period of n. Okay, so you can, by doing this, you can construct any number of periodic non-physical solutions, whatever you want. So these are well known in literature, but what is not really well known is that there is a third type of non-physical solutions. Non-physical solutions. I call it type 2, and I call it quasi physical solutions. The reason it's called the quasi-physical solutions is because it looks like physical solutions, but is not a physical solution. And the reason it looks like a quasi-physical solution is because it is not periodic. Right? So if you get a solution whose trajectory looks chaotic, that's actually quite easy in the sense that it never repeats itself, right? It looks like it's doing random things. That's actually what a chaotic solution usually looks like, right? But what this type of non-physical solution tells you is that even if a trajectory looks like it's chaotic, it never repeats itself, it keeps doing new things, it might not be physical. So let's give an example of that. Remember, we said that if you choose an arbitrary number, arbitrary real number from between 0 and 1, right? That number is almost surely going to have infinitely many digits, and its digits always have a probability of being 0, with half a probability being 0, half probability being 1. What if we choose a number that also have infinitely many digits, whose digits are also independent from each other, but it has a small probability of being 1 and a higher probability of being 0? Okay, so what if we choose x1 equal to point x11, x12, etc., where x1k are IID and with 0 and 1 with probability p and probability 1 minus p. So p, if p is exactly 0.5, then this is a typical number, right? But if p is not 0.5, this is a number that you can still get, but you would get with almost a zero probability. Okay, you can actually show that the set of all such numbers whose p is not equal to 0.5 are actually a measure zero set. All right, so now if you choose such an initial condition, and then you keep applying the map, right? You keep shifting the numbers to more and more significant digits. What happens is that for any xk, shouldn't use k, for any xi would be equal to point xi1, which is point x1 with 1 plus I, right? x2 with x1 with 2 plus I, etc. So the digits are still chosen from the infinitely many digits of the initial condition. So they are still IID, right? And they still have the probability of p and 1 minus p being the probability of every digit. So after you shift it for a long time, what is the probability that the very first digit is 0? It's p, right? And that means if you look at the distribution of a very, very long trajectory, what is the probability that what is the histogram look like on the left half of the histogram? So if you do a histogram between 0 and 1 of the long time solution, right? Instead of being uniform, what is the likelihood that the solution, any solution in a very long trajectory, is on the left side of the 0-1 interval? What? It's p, right? So let's say p is less than half, and on the right hand side is more than p, right? Okay, so we know on average this is p and this is 1 minus p. Oh, actually, right. So this is actually the height is actually 2p, right? And the height is 2 minus 2p, right? Because we are looking at we are looking at the PDF, right? So it's the probability divided by the width of the interval, which is half. Okay, then let's look in more detail again. How about the second digit? What is the likelihood the second digit is 0? Again, is p, right? And it is independent of the first digit. So the two-digit series being 0, 0 is actually p squared. And the two digits being 0, 1 or 1, 0 is actually p times minus p, or 1 minus p, right? And the two series being 1, 1 is 1 minus p squared. That would also, if you look at the histogram, instead of 2 bins, if you make it 4 bins, you would get a even lower one on the left, and the two middle ones would be 1 minus p times p would be times 4 would be less than 2. So you would get something like that. You get a histogram like that. And if you zoom even finer, you're gonna get a histogram that basically the finer you zoom in, you get more structures on the histogram. So at the end, if you visualize if you visualize the histogram, you should see actually a fractal structure, right, for its probability distribution. So this is exactly contrary to what we have proved the last time, right? So remember, how did we prove that the long time distribution is a uniform distribution? we started with the PDF that is smooth, right? That has a derivative, and we proved that for every iteration, the derivative of the PDF has to decrease by a factor of at least 2, right? So if you don't remember, like I can show you. So essentially, if you have a PDF like that, and if you take so this is the PDF of xi of xk, no xi, and you take the next iteration, the so let's say row of xi, and the row of xi plus 1, if you take the derivative, right, is going to be less or equal to the derivative of row at the previous xi1. So basically every xi plus 1 is mapped from two possible previous values, right? Plus row prime of xi2, both divided by 4, right? Because every time you map a PDF, the height is decreased by 2 and the width is increased by 2. So the derivative actually decreases by a factor of 4, right? So then you use the a simple inequality, you get basically less than half of the maximum possible row prime of xi, right? So if you then take a maximum over the row prime of xi plus 1, you show that the maximum derivative would always decrease by at least a factor of 2. All right, so that is in stark contrast with this, which tells you that you actually not only don't have a uniform distribution, you actually have a distribution with no derivative, right? A fractal structure. Okay, so this is an example of a non-physical solution that looks physical, right? That if you look at the trajectory, it instead of, if you don't focus on the histogram, just look at a trajectory, you would see it never repeats itself, right? It just keep doing new things, and there are new series keep popping up, but this is nevertheless a non-physical solution.
So I kind of have a question on this, because it seems baked in that you know the answer you want at the end. So if you're just given some random system, how would you tell that it was supposed to be a uniform distribution instead of weighted like you're talking about?
Yeah, so this is on a very particular example, and for us to really understand what potentially different solutions are, and what the real goal of introducing this example is, then we look at shadowing. What happens when we look at a shadowing solution, right? How likely are we gonna get a shadowing solution that is physical, and how likely are we gonna get a shadowing solution that is non-physical? And one thing in particular is that we see that this kind of non-physical solutions, particularly the kind of quasi-physical solutions, often has a fractal distribution in its density. And we'll actually see that when we compute the shadowing solution of not just this particular system, but a shadowing solution of more of other systems, and we can still see the fractal structure of its PDF. Mm-hmm. Okay, and so let's look at shadowing. Are shadowing solutions physical, non-physical, or quasi-physical? And the answer is it can be either physical or quasi-physical, right? We just can't tell. So let me just give you an example of a quasi-physical shadowing solution. Okay, so we were still looking at the sawtooth map, right? So, but instead of the values rising to 1 at the half point, so let's look at the solution that rises to, let's look at the different map that rises to 1 at the value of a p that's between 0 and 1. So our previous sawtooth map rises to the value of 1 at 0.5, right? And then rises to 1 again. So here let's look at the perturbed sawtooth map that goes up at a slower slope, at a slightly less than a slope that's less than 2, right? Instead, it goes up by 1 over p, and then at the later section of the map, it rises at another linear slope, right? 1 over 1 minus p. So when p and 0.5 are very close, when p is very close to 0.5, the two maps are very similar, right? So you can say that a solution that satisfies the red governing equation is a pseudo orbit of it's a pseudo orbit of the system governed by the green trajectory, right? Make sense? Okay. Now let's look at now let's pick a solution x1, x2, etc. Satisfy the red map. So let's say the red map is phi red, and the green map is phi green. All right. Or let's actually don't use a color. Let's just use the probability p. So the red map is phi p, and the green map is phi 0.5. All right. Okay. So the red basically satisfies phi k, xk plus 1 equal to phi p of xk. And let's denote a green solution that is y, and yk plus 1 is equal to phi of 0.5 yk. Okay, so because the sawtooth map is a map that satisfies the shadowing property, right? We know that if we have let's say if we take a arbitrary, let's take a physical solution to the red map, to phi p. And of course there exists a shadowing solution y that satisfies the phi 0.5, right? So the question is, if xk is a physical solution, is yk a physical solution? All right, that's the question we want to answer. And we actually know, remember we derived the formula for computing what is yk, right, from xk. We just start from the very last solution xn and just trace backwards, right? Okay, and in this case, if we do that, we can actually obtain exactly what yk is. And I'm going to write down the formula, all right? So let's represent, let's actually represent xk, no, it was red. Let's represent xk is equal to a summation of, sorry about the index. I think let me just change this index to I, and I just want to be consistent because I used the k to represent the digits in the previous slide, so I just want to keep using I as a index to the solution, to the time, and use k as yeah, let's use k as the digits. So if xi is a summation k goes from 1 to infinity, xik times 1 over 2 to the k, right? So what is that? That is actually a binary representation, right? Xi k is either equal to 0 or 1. So So that is actually what we mean by a binary representation, right? So k would be xik would be the kth digit. So the first digit xi1 represent am I in the left or right half of the interval 0, 1, right? The second digit is going to be multiplied by 1 over 4. The third digit multiplied by 1 over 8. Okay? But let me actually use a slightly different representation of this. Okay? I'm going to, instead of using exactly half, I'm going to represent it by the following. I'm going to be multiplying it by what I call it, let's see, let me call it AK. So what does this AK mean? The AK means, so let me first represent what A1 means. So A1 is exactly equal to P. So if the first digit is equal to 0, okay, it means that this number is in between 0 and P. If the first digit is 1, it means the number is between P and 1, right? So this is a slightly different representation as the binary digit series, in the sense that if P is exactly equal to 0.5, this is going to be exactly equal to the binary representation. But if P is different, it's going to be different. And what does A2 mean? A2 actually would depend on both P and the first digit. So A2 actually is a function of P and xi I1, right? It is going to be either P squared or P times 1 over P. So it is equal to P squared if xi1 is equal to 0, or P times 1 minus P if xi1 is equal to 1. So what does that mean is that A2 represents after you use this map and map the xi once. Is my xi plus 1 lying on the left half of this interval from 0 to P, or does it lie on the second half from P to 1? All right, and in general, AK, which depends on P, and xi1, etc., all the way to xik minus 1, right? It is going to represent after you use this map to map for k minus 1 times. Is this number going to be on the left or right of this interval? Okay, represents is sized such that the corresponding digit xik represent if I map for k minus 1 times, is it less than P or greater than P? All right, so if so 0 means after you map for k minus 1 times is less than P. 1 means if you map for k minus 1 times is greater than P. Okay, so this is, as you can see, this representation when P is equal to 0.5 is exactly the same as the binary series representation, right? But for P different from 0.5, this is still a binary representation, but a binary representation that differs from the traditional binary traditional definition. Okay, then I'm going to tell you what is the shadowing map. Xi would then be exactly equal to yi is going to be exactly equal to infinite series of exactly the same xik, but then multiplied with 1 over 2 to the k. So exactly the same traditional binary representation. All right, and now you can see why they are shadowing solutions, right? First of all, it's relatively easy to prove that because of the whole construction of the definition of the xik's are defined according to this perturbed map. You can easily show that the xi actually satisfy exactly the perturbed map. So phi p. That's no problem, because every time you apply the map, actually you are shifting this xik, right, on the left by 1. So this yi, right, because it follows the same xik, but using the traditional definition, this yi is also trivial to prove that it satisfies the traditional sawtooth map. So xi satisfies this map, yi satisfies this map. And they are shadowing solutions. They differ from each other by a very small amount if p is very close to 0.5, right? This can also be seen from the definition. So for example, if p is very close to 0.5, then all of these a's are going to be very close to 1 over 2 to the k. So you can show that xi and yi, they differ by a number that scales proportionally to the difference between p and 0.5. They are shadowing solutions. Okay, now let's consider what is yi. Is yi a physical solution or non-physical solution? The answer is that yi is not going to be a physical solution. Why? Because think about the perturbed map. What is going to be the equilibrium distribution of the perturbed map? Well, it may not be obvious from the first sight, but the equilibrium distribution of the perturbed map is still a uniform distribution. You can use exactly the same proof as we applied for the original sawtooth map, right? So essentially the probability distribution from 0 to 1 of the k+1th iteration is going to be a linear superposition of a distribution mapped from the left, not half, but the p% of the space, divided by, well, in this case, not by 4, but multiplied by p squared, right? And then added to the probability distribution on the right half, multiplied by 1 minus p squared. Okay, so as long as p is close enough to 0.5, the derivative still would shrink. The derivative of the sum of the two probability distributions would still be shrinking enough that the final distribution is always going to have a 0 derivative. Okay, so the distribution is still going to be uniform. What that means is that if you use this particular representation to represent any number, any physical trajectory, right, which is distributed uniformly between 0 and 1, that distribution would have solution would have half probability of, not half probability, but p probability of between 0 and p, right? And 1 minus p probability of being in between p and 1. That means, what is the probability distribution of xi1? xi1 would have a, which means the first digit in this representation, right, would have a p probability of being 0 and 1 minus p probability of being 1. Right, remember the AKs are exactly sized so that after k minus 1 iterations, right, would that number be less than p or greater than p? Right. So essentially, xik is after k minus 1 iterations. Is that number going to be in this region or this region? And we know that the probability that the number is in the left portion is exactly p, right? Because the distribution is uniform. So what that means is that the probability of xik equal to 0 is always going to be p, right? No matter what I and k is. Okay? And therefore, after you fit it into the definition of yi, we actually get exactly the non-physical, the pseudo, the quasi-physical solution we manually constructed in the previous case. All right, so basically this is an example where we can mathematically prove that a shadowing solution is a non-physical solution. We can mathematically construct what the shadowing solution is, and it is a quasi-physical solution. Okay, so the real question is this general or not? Right, so for this, we actually constructed a series of other mathematical and analytical examples. So this is not the sawtooth map, but the tent map. So instead of going up and up, it goes up and down. And we have here this example, we are doing similar kind of perturbations, right? Perturbing the center point of the tent map. And again, we can show that the uniform distribution is the equilibrium distribution of both the blue and perturbed maps are uniform. And here, by computing the shadowing solutions, we get a distribution like that. So these are different amount of perturbations. This is a smaller amount, this is a larger amount. The actual physical distribution should be uniform, but the shadowing distribution is something like this. All right. And this is an example where we perturb it in such a way that the maps are no longer straight. And again, we can show that if the reciprocal of the derivative here and the derivative here adds up to a constant, then the equilibrium distribution should again be uniform, right? And here is the distribution of a shadowing solution, and this is the distribution of a physical solution simulated by from an initial condition as opposed to a shadowing solution. So this is a case where we perturb it in a different way, and this is a shadowing solution and a physical solution. Very different. And again, like we change the top to be different, and this is actually, I think, yeah, so this is the shadowing solution, this is the physical solution. So different. And now this is for a different map. So this is actually the Lorentz map. So instead of the tent map, this is a map extracted from the Lorentz equation. And we made the perturbation in the 3 parameters, I think sigma, rho, and beta, right? And shadowing solutions, physical solutions, shadowing solutions, physical solution of the perturbed systems. And this is the last one, shadowing solutions, physical solutions. So a remarkable feature is that the shadowing solutions all look fractal, right? And the physical solutions that we can see, like we can actually prove that the physical solution in the unstable direction should have a non-fractal distribution. So this is really saying that we should be very careful with what we can infer from shadowing solutions, right? We cannot really show that a numerical simulation actually would reproduce the statistical behavior of a real physical system just through the shadowing argument. So how can we understand exactly how stable the statistics of chaotic systems is? right? That is a big topic of discussion for the remainder of this semester. It's not, it's far complicated than just from the concept of shadowing. Okay, I will see you on Wednesday and continue on this topic and see what we can do without using shadowing. Okay, thanks.